Okay, so just let's remind you that t plus a, the reference point, plus tr is a direction. I mean, you can put you can cover all of them it's a way to go to the efficient frontier. It's a way to search the efficient frontier. So I explained that those scalarization problem is a weak multi-objective programming in the previous lecture, so that you understand the motivation. We have different cones: convex cone, polyhedral convex cone. This is really important for today because we want to prove a theorem. And non-convex, for example, if it's inside the cone, this is inside the cone, then the points here are not inside the cone. So it's not a convex, so it's a non-convex. And also, if you use, for example, Koletsky decomposition in Markowitz problem, you can come up with very interesting formulation. And these are polyhedral cones. And so you see that we want to find the cone using trying to approximate it by to define it by convex polyhedral cones. And so we want to go to higher dimensions. For example, here, sometimes we want to go to higher dimensions. We have three objective functions, so m is 3, and here m is 4, because we have 4 objective functions if you multiply it by k. And that's the essence of this theorem. I want to show you how you can find those weakly minimal points that I described in my previous lectures in the proof of that theorem, and how we can systematically find those weakly minimal points, so that we just use that theorem. So the problem is that you want to find some hyperplanes, because you don't want to go to all of this space. You don't want to search A in all of your space, because it is a curse of dimensionality, and the order of complexity is really high. For example, computer scientists may say that this does not work. It's NP hard. And that's why we use such theorems in order to say that, for example, we just need to focus and restrict the parameter space, parameter set on this. So we choose, it's enough to choose A on this hyperplane. So it covers all the important search directions. And so this is the big motivation for understanding what we are doing, actually. So in a weighted sum approach, you could use these points to go to the direct. But let's prove this important lemma. So if we have such cone that is defined by some finitely generated, it's a polyhedral that is finitely generated. And we want to prove that if xj is a minimal solution of this scalar optimization, which is easy, then xj is definitely a weakly k-minimal point. And in the next part, the second part of the theorem, it says that we can now use aj and tj such that this one is a minimal solution of SP. So let's just start by the first part. The first part says that we want to find so k is the of all y such that Li transpose y is greater than 0 for all 1 to s. So the theorem says if xj is minimal, if it is minimal solution of minimization problem of Lj transpose of f of x, which I said it's easy because it's a scalar optimization, then the theorem says, we should prove that xj is a weakly k-minimal point. So I use proof by contradiction, as I always do. Proof by contradiction. So I assume no, xj is not a weakly. So xj is not a weakly k-minimal. And it means that, okay, so y bar minus interior of k, intersection of that of f evaluated on the decision space is equal to 0. And so we can say that y bar it does not belong to f of x plus interior of k. And then I say, okay, so f of xj is inside f of x plus interior of k, because I'm doing just proof by contradiction, and just if I just subtract that from f of x, it's easy to see that it is inside interior of k, and that's why we are allowed to use this multiplication in the theorem if of xj bar minus f of x is greater than 0. And so Lj transpose f of xj bar is greater than Lj transpose f of x, and this is a contradiction. Why? Because we have assumed that xj bar is a minimal solution. So I just want to prove the second part of that. So let's just go and prove the second part of that. So the second part says that if A is equal to aj bar and you define it such that it is f of xj bar minus tjr and Lj transpose r is greater than than 0, and if you just define tj by b transpose f of xj bar minus beta divided by b transpose r, the theorem that we want to prove is that it is a minimal point. tj and xj bar is a minimal solution, of sp of aj bar and r. So I want to prove that. So already xj is a feasible solution, because if you just write this one minus f of xj bar, it is 0. And that belongs to k, so no problem, it's a feasibility. But I want to prove by contradiction. So I assume that no, tj bar and xj bar is not, again by contradiction, is not a minimal solution. Okay, is not a minimal solution. You mean that there exists another t prime and x prime with t prime is less than tj because it is minimal. It is another it is a better minimal, and because of feasibility, I can write aj bar plus t prime r minus f of x prime is inside k, and from definition of a j bar, I can say that f of f of x bar j minus t j bar r plus t prime r minus f of x prime is inside k, and just multiply both sides by Lj transpose. So I mean this one. If I just multiply by Lj transpose, this one, all of this one, then this one is greater or equal to 0, and that means that Lj transpose f of xj is greater or equal to Lj transpose f of x prime plus tj bar minus t prime Lj transpose r. Because this one is greater than 0 and this one is greater than 0, because we said that t prime is less than that, then the overall things is greater than Lj transpose f of x prime, and this is a contradiction. It's a contradiction to xj bar that is a minimal solution of 2 points 2.12. So we have proof that the second part of the Lemma 2.12 holds.